Welcome to Programming with Professor Califf. Today I'd like to talk to you about types in Java. So in the last video we talked about how in order to interpret the memory that's set aside for a variable correctly, we have to know what type that data is supposed to be. We know that num lives here is 3 because we know that it's an int. We know that height is 2.5 because we know that it is a floating point number. We can interpret the value for grade correctly because we know that it's a char. So today I'd like to talk in a little bit more detail about what we call the primitive types in Java. There are 4 categories of types. The largest of those is the integers. We actually have 4 different kinds of integers available to us. Then we have floating point numbers, which, as I mentioned before, you can think of as kind of like real numbers, characters, and then Boolean values. We'll start with the integers. These are exactly the same thing they were when you learned about integers in maybe an algebra class. They're whole numbers, positive, negative, and 0. As I said, we have 4 different types. The differences among those types have to do with the size in memory. So how much memory space does this variable take up, and the resulting range and values. Our 4 types are byte, which is the smallest. It takes up only 1 byte, which is the same as 8 bits of memory. So its minimum value is negative 128, and the maximum value is positive 127. And that's actually based on 2 to the 7th because we have 8 bits. Shorts have a larger range, negative 32,768 to positive 32,767. You can see that that's related to 2 to the 15th, and that's because there are 16 bits. Ints have 4 bytes, 32 bits, and a correspondingly larger range. And longs in Java are quite large, allowing us to go from negative 2 to the 63rd to positive 2 to the 63rd minus 1. I'm not going to read out the number, but you can see it there on the screen. Now, when we want to use these integers, we will need to assign values to them. You can always assign what we call a narrower type to a wider type. So if I have a value in a short and I want to assign it to a long, that's just fine. We can't assign wider types to narrower types, at least not without telling the computer it's okay. So I can't take a long and assign it into an int unless I tell the computer, hey, let me do this. We can assign an integer literal to any variable where it will fit. If the value is small enough to fit in a byte, I can assign it to a byte. Let's actually try this out a little bit. So I have here the program that we were working on previously. Be sure to go ahead and pull this up. I encourage you to pause, go get it all set up so you can follow along. You're not going to learn this if you don't do it. Just a reality. Okay, so I'm going to make some modifications. I'm going to leave num students as it is, but I'm going to change num lives to be a byte, since that's usually very small values. And we'll go ahead and make that 3 right away. Then we don't need any characters right now. So let's go ahead and make a short, which I'm just going to call num stuff. And I'm going to set that to 200. And then I want a long, which I'm just going to call very large number. So I'm going to put a lot of zeros here. And you'll notice I've underlined. That's because Java assumes that your number is an int unless you tell it otherwise. So now I'm going to add an L. Notice I use a capital L. You could use a lowercase l, but most people will use a capital L because it's much easier to distinguish from a number. So this wasn't a valid integer value with all these zeros, but it is a valid long value. Once I add the long, then Java quits complaining. Okay, now I'm going to take out some of this printing and so forth because it's not all valid and we're not doing these things. So what I want to focus on is doing things with these new values that I have. First of all, let's take a look, and we see that if I say byte is num lives is assigned num students, it's going to complain about that. Now, num students has the value 20, so that's a valid value. And notice that if I do this with the value 20 instead of num students, that's just fine. But remember, we're not supposed to assign narrower types the values that are in wider types. We can go the other way. So if I try to say num stuff gets num lives, that's just fine, but not this other way. However, there is a fix for it. It's called casting. And in that case, I just say, hey, this is fine. You can do it. And if I then run that, we see that it works just fine. Now notice that we do have to be careful. So I'm going to try the same thing with num stuff. I've told it, num stuff, we're fine. But notice that 200 is bigger than 127, which is what we said was the largest value we could have. So let's see what happens when we try to run this. We're going to get minus 56. So we have to be very careful when we're doing this casting thing to make sure that we have values where it will actually work. Let's also just demonstrate that if I've got the widest type of these, I can assign any of these things to it. So num lives, num stuff, num students, very large. And all of these things are fine. So all of these smaller types can be assigned into the bigger type, the narrower type into the wider type. But the other way around, we have to do the casting. And if the value is too big, we will have a problem. And let's go back and talk a little bit about our next kind of number. Okay, so the next type of number I'd like to talk about is floating point numbers. These are kind of like real numbers, but not exactly. They do accept values that have decimal points. So what we actually have is something like scientific notation. So in school at some point, you probably have learned about scientific notation, also sometimes called exponential notation. And what we do here is we have an exponent, a value times 10 to the 12th. So the value times 10 to some exponent. And this value that we're multiplying is called the mantissa. So the idea of floating point numbers is that instead of storing a binary representation of the whole number, we're going to store a mantissa and an exponent. The bytes used for the floating point number, part of them are going to be used for that mantissa, and part of them for that exponent, which will actually be 2 to the something as opposed to 10 to the something. We have two floating point types. One of them is float, which stands for floating point number. Its size is 4 bytes, and the positive range is 1.4 times 10 to the minus 45th through 3.4028235 times 10 to the 38th. And then there's a corresponding, very similar range of values on the negative side. The second type that we have is the double, which stands for double precision floating point number. So as you might expect, its size is 8 bytes, and its positive range goes from 4.9 times 10 to the minus 324th. So very, very, very small. To 1.7976931348623157 times 10 to the 308th. So as you can see, quite a large range of values available. And of course, there's a negative range that is similar. Now, when we think about floating point numbers, one of the things we always have to be aware of is their accuracy. They simply cannot always be accurate. You're actually probably familiar with this concept. So if we think about 1/3 in decimal, 1 divided by 3, 0.3333333333333, etc., 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 never ending. If we have to somehow keep that in a certain number of digits, then we're going to be inaccurate because we're going to be missing the rest of the 3333333s. Similarly, we have a problem like that in our floating point numbers. The mantissa, that number we're multiplying by 2 to the something, only contains a certain number of bits. So it can't represent a number that goes beyond that. It's also worth noting that what's inaccurate in base 2 in the computer is not always the same as what is inaccurate in base 10. So there may be numbers that you're expecting to be very accurate, but simply aren't because we're dealing with base 2, not with base 10, the one we're used to. So just never trust your floating point numbers to be perfectly precisely accurate. When we go to assign floating point values, we have the same rules of wider and narrower types as we do with our integers. Note that float and double are both wider than all of the integers. So I can assign a long into a float and obviously the smaller ones as well. However, it's worth noting that you may lose some accuracy when you go from an integer to a floating point number. Numeric constants with a decimal point in Java. So if I write the number out, it's going to be interpreted as a double unless we have an F either lowercase or capitalized after it. Similar to how we assumed that a constant integer was an int unless we specified that it was a long. So 19.5 is a double, 19.5f is a float. We can write exponential or scientific format in code. This can sometimes be really helpful if we're dealing with very small or very large numbers. The way that works is we're going to replace that times 10 with an e. So 3.8 E14 is 3.8 times 10 to the 14th. Now we are writing in base 10. So that is times 10 to the 14th, as you would generally expect. 2.3 E minus 20 would be 2.3 times 10 to the minus 20. So if you're needing to deal with these very large or very small values that you might find, say in a scientific application, you can do that much more easily by using this exponential format. Let's jump back over into our code and try out a little bit with the floating point numbers. Let's go ahead and add a couple more variables here. We'll add a float. Num is 3.14. Now here, notice that if I just say 3.14, that is an issue, and it says type mismatch cannot convert double to float. So this is why we need to add the f. That makes this a float value as opposed to a double value, and that's just fine. Then let's go ahead and create a double num, and I'm going to make that a very, very, very small number. Now I do want to see what happens when we print these before we work with them some more. So system.out. I'm not going to worry about label on these. We're just going to go ahead, float num, and double num. So let's run that. Now I do want you to notice here, by default, that very small number is going to be printed in exponential notation. Later on, we'll talk about how we can format our numbers and decide how they're going to be represented. But by default, anything that is very large or very small will be printed in the exponential notation. let's demonstrate this actually by just saying double num gets a very large number. Remember, we can do this, and I'm going to do the same thing with float num. And let's run those. Now, one thing I want you to notice here, we put the same exact values into a float and into a double, but they are not the same. So one of them ended up interpreting the number as having this 0.000001, whereas the other did not. The double, which is higher precision, came out more accurate than the float. But this is a good way for us to recognize that floats and doubles don't necessarily have a lot of accuracy. So I'm going to actually print out the result of comparing these. So system.out.println float num equals double num. And we're going to see that what gets printed is false right here, because these two numbers are not the same after we put them in floats. Now, if I create a second very large number, so large 2 is very large number, and I'm going to do the same thing with very large number and large 2, then run that, and we see that the floating point numbers do not have the same, are not the same. They are not equal, but the integer values are equal. This is something that is very useful to remember from the beginning when we start to compare numbers and try to make decisions. We have to be very careful when it comes to our floating point numbers, not to try to check if they're exactly equal. So we'll talk about ways to handle that. Notice also, so I'm going to make float num have just a regular old number in it, an int. Then I'm going to try to assign that into num students. And again, we can't do that because of the type mismatch. Now here we can again do the casting. So let's see if that all works correctly. We do end up with num students printing as 7. Now I want to demonstrate something else. If I get rid of that assignment to 7 and just try to assign the 3.14 in, but do this cast to an int, let's see what's going to happen here. What happens is num students will be 3. When we do that casting, if we're taking a floating point number to an int, or any integer value, then we're going to just throw away everything after the decimal point. And I do mean throw away. So let's actually make this 7.99. And run it again. And we see 7.99. That would round to 8, of course, but we're not rounding here. We're truncating. So we're just going to throw away the 0.99 and get just the integer part of the value. Let's go on back to our slides and talk about the last two types of interest to us. So we have characters, and we've seen characters a little bit. We call them char or char. This is a Unicode representation. So if you've heard of Unicode, that's a more extended character set that lets us handle lots more values than the original ASCII, if you've heard of that. In Java, Unicode characters are 2 bytes, generally speaking. And character literals are going to be enclosed in single quotes, just like we've seen in our examples in previous videos. There are some special character codes that it's good to know about. This is not a complete list, but these are the ones that will be most important to you, most likely. The \n represents the new line, so that character that tells us, hey, we're going to the next line. \t is a tab character. \\, since we're using the \/ to make these special character codes, we do have to have one for the \/ character because sometimes we need it. \single quote is if you want to have a single quote and you're already inside single quotes, that lets you represent a single quote. And similarly for the double quote. I want to make a quick comment about strings. So we don't usually use characters one at a time. We have various uses for that, but it's much less common than using lots of characters in a string. We're going to cover the string type a little later, but I do want you to be aware of 2 things now. First of all, strings are made up of characters. So understanding what a char is will help you understand strings because strings hold chars. Second, when we have a string literal, it's going to be enclosed in double quotes. So in Java, you can tell the difference between a char, which always has to be just one character, and a string, which could have 1 or more characters or even 0 characters, by looking at the type of quotes. So this is not true of some programming languages. Some programming languages don't distinguish between single quotes and double quotes. Java is one that absolutely does. Single quote A, single quote is the character A, and that is not the same as double quote A, double quote, which contains the character A, but is a string that has just one character, the character A. Our last type is the Boolean type, which is spelled Boolean lowercase. It has 2 possible values, which are true and false. This we'll see quite a bit when we move on to making decisions in our programs. Thanks for watching. I know that was not a super short video, but I hope you now have a better understanding of types and the kinds of variables that we can have in Java. Next video, we're going to look at how to name things well in Java.